Super buildings are generally constructed in the sequence of planning, foundation, stacking, finishing, and mechanical systems. Following this process, we previously examined the matte concrete foundation of the Yokohama Landmark Tower, and in the last session, we discussed its structural design. Today, we will focus on the stacking process, how the building was vertically assembled after the foundation to realize a superstructure.
Does that sound like something you'd be into? I believe the truth can be reality. Will you roll with that? 'Cause I want you to.
In structures like the Yokohama Landmark Tower, which adopts a tube-in-tube system, it is common practice to construct the central core first. By building the core ahead of other elements, the primary structural frame of the building is secured early in the process. This early establishment of the core provides overall structural stability and serves as a reliable reference point for the construction of the outer structural frame and subsequent phase. The core, which functions as the inner tube, typically contains key vertical circulation and service shaft, including elevator shaft, stairwells, and mechanical ducts. The completed core also provided the base for crane installation and climbing operations, securing a vertical transportation system for concrete, material, and personnel during construction. At the Yokohama Landmark Tower, 4 Megatower cranes, JCC series Jeep-type climbing cranes, were installed at the four corners of the core. This configuration enabled maximum working radius coverage across the entire building footprint, allowing for the efficient lifting of large components, such as steel frames and exterior wall panels, to the outermost areas of the structure. The working areas of the cranes were carefully arranged to avoid overlap and minimize interference between them. This coordination was essential for enabling simultaneous crane operation, thereby improving overall construction efficiency. As seen in the site layout plan, material stone yards, such as the UF fabrication yard and general storage areas, were placed within the jeep radius of each crane to optimize logistics and minimize transfer distances. Using these cranes, the Yokohama Landmark Tower lifted steel frame units, exterior wall elements, and MEP components throughout the building process. Structural components were lifted and assembled in 3-floor units as part of the stacking process. The Yokohama Landmark Tower was constructed by stacking 3 floors at a time, a method suited to the unique challenges of super constructions. In such buildings, each floor must gradually support the accumulated load of dozens of upper floors. Since concrete does not immediately gain its full strength after placement and typically reaches design strength after 28 days, this method was carefully calibrated. The Landmark Tower employed a hybrid structure system with SRC, steel reinforced concrete in the lower levels, and steel structure in the upper levels. In the SRC zones, achieving sufficient concrete strength was critical, not only for resisting axial compression, but also for shear and fracture strength development. If the stacking units had been too large, the upper loads could have been applied before the concrete had adequately cured, making the structure vulnerable to creep and other forms of long-term deformation. The 3-floor unit was considered the minimum safe interval that could ensure both continuous load transfer and structural integrity during construction. In high-rise structures, wind load often constitute the most significant components of the design load. By completing the structure in 3-floor stacking units, each block functions as a minimum toughness unit capable of resisting lateral forces. This approach helped maintain consistent composite behavior with the tube-in-tube system, preserving the building's overall structural stability throughout construction. The climbing cycle of the tower cranes was synchronized with the 3-floor stacking sequence, with one lift occurring every 3 floors. This regular interval was a key factor in maximizing crane operation efficiency and maintaining overall construction process stability. Each stacking cycle also served as a critical checkpoint for correcting verticality, horizontal alignment, structural spacing, and facade positioning, making the 3-floor unit an ideal rhythm for both construction, accuracy, and process control. Steel frame units were lifted in 12 to 15 meter blocks, significantly reducing on-site welding and assembly time and minimizing high-altitude construction risk. Following the structural components, MEP units, exterior wall panels, and cotton wool modules were lifted and installed. On average, 68 major lifting operations were carried out per day. The maximum weights of individual units were approximately 65 tons for steel frames, 1 ton for exterior panels, and 24 tons for curtain wall units. Because on-site work was minimized, precise placement of each unit was essential. This was achieved using a CAM-based 3D alignment system known as the erection box. The erection box played a key role in automating or semi-automating the alignment of beam to column connections, improving welding quality and controlling installation tolerance. In effect, it functioned as a high-precision assembly station, ensuring that each structural component arrived on site in a perfectly pre-aligned condition. After each unit was placed, concrete casting for the previously stacked section was carried out. The Yokohama Landmark Tower implemented a system to pump lightweight concrete directly to a height of 296 meters without using intermediate relay stations. On the left side pump line were 2 elbow bands increased pressure loads. A higher capacity pump I with a maximum discharge pressure of 180 kg per cubic centimeter was installed. In contrast, pump S had a lower maximum discharge pressure of 135 kg per cubic centimeters and was used in a more favorable routing condition. All delivery pipes were 5B type with an inner diameter of 125 mm. Considering the high internal pressure in the lower sections, high-pressure steel pipes with 9 mm thickness were used up to height of 200 meters. The surround value were determined based on both the required discharge pressure and the flowability of the concrete. Up to the 20th floor is 18 cm. Floors 21 to 61 is 21 cm. Floors above 62 is 23 cm to ensure high workability. For pressure loss estimation, an internal pipe friction loss of 0.135 kg per square centimeter per meter was assumed. The pumping route was modeled with up to 3 90-degree bands at ground level and 3 additional bands at the casting floor, each with a 1 meter radius. Under these conditions, with a discharge rate of 40 cubic meter per hour, the required pumping pressure was calculated to be approximately 120 kg per square centimeter. Even when applying a safety margin of 1.25, the estimated required pressure was 150 kg force per square centimeter, which remained below the maximum capacity of 180 kg force per square centimeter. Therefore, direct pumping to the top floor was considered fully feasible without the need for relay station. In super buildings, exterior panels, particularly glass curtains, require not only structural support for their weight and size, but also precise control to withstand wind-induced sway and rotation at high altitudes. To address these challenges, the Yokohama Landmark Tower incorporated several specialized technologies. During lifting operations, materials with large surface areas relative to their weight, such as facade panels, are highly susceptible to rotational movement around their vertical axis under wind pressure. This unintended rotation can complicate installation and significantly reduce productivity. To mitigate this issue, a new lifting device was developed, equipped with thrust mechanism to actively control and stabilize the panel orientation during hoisting. The lifting device was equipped with two fans attached to the suspended rod, such as a curtain wall panel capable of generating thrust forces to actively control the rotation of the panel around its vertical axis. When wind acts on the panel during hoisting, it induces lift and drag forces, which in turn generate rotational torque about the vertical axis of the rod. The developed system counteracts this rotation by producing opposing thrust forces via the onboard fans, allowing for active orientation control of the panel during installation. To improve MEP construction efficiency and reduce the overall construction period, the Yokohama Landmark Tower employed prefabricated MEP units in 3-floor modules. These large prefabricated MEP units were hoisted by crane and inserted directly into their designated position. Over a relatively short construction period of 39 months, a total of 62,000 tons of steel, 40,000 tons of rebar, and 310,000 cubic meters of concrete were used to complete the 73-story structure. The following chart summarizes the overall construction sequence, showing how each phase, beginning with foundation concrete placement, followed by steel erection, concrete casting, facade installation, and interior finishing, was organized. Let's now take a closer look at the detailed construction schedule. The construction schedule shows that various operations were meticulously coordinated in parallel on a floor-by-floor basis. The following segment of the schedule corresponds to November 1st, 1991. From the 35th to the 37th floor, the steel structure framework was being erected, while on the 25th floor, 10 levels below, concrete placement work was underway. On the 18 floors, exterior cladding and glazing work was in progress. And on floors below in the 15th, interior finishing work was being carried out. Construction began with the core using a 3-floor cycle that set the project rhythm. Prefabricated steel frames, facades, and MEP units were hoisted and aligned with high precision. Concrete placement followed strength and pump limitations, while wind control systems stabilized panel installation. Structural, mechanical, and finishing work advanced in sync floor by floor. Stacking was not a repetition, but precise, integrated execution. Next week, we will talk about the finishing, building services, and maintenance of Yokohama Landmark Tower. based on my own site visit and observations.